Good morning, friends. This is Professor Chaubey's physics class. Myself, prof.a.k.chaubey. Today we will discuss transient currents under the heading Physics Made Simplest. So far we have discussed constant current or DC current, one directional current, and we talked about the Kirchhoff law and the other circuit analysis methods, writing the Kirchhoff voltage law, current equation, etc. We have done some problems also. Now I want to discuss transient currents. First I will explain you the transient currents. Say I have made a circuit here. This is battery E, this is switch S, and then the resistance, and this is the inductance coil. You know inductance coil, where we have coil wire in the circular shape, many turns, that is called inductance. So when we press the key and make circuit on, what happens? The current will flow in the circuit. How the current behaves, how the current changes, how the current, whether the current reaches maximum in a small time or more time, what etc. So all these things we will discuss. So transient current means not constant current. Transient currents at one particular time. So time dependent of the current means current is not constant. Current is either increasing or decreasing, whatever depending upon the condition of the circuit, but it is not constant. It is transient, means time dependent. So time dependence of current here, this is the circuit. Remember, when we press the switch, some current, say I, is flowing in the, when the current I flows through the inductance coil. What is the property of inductance coil? Inductance coil opposes the growth of current. If current increasing, it produces induced EMF. By current, changing current, magnetic flux will change to the inductance coil, and due to Lenge's law, there is induced potential. Induced potential is proportional to di dt, that is the current rate of current changing. Current changes as di dt, means time dependent of the current. How the current is building up, how the current is changing in the circuit with time. So inductance, that we have this induced EMF is proportional to, say, di dt, the rate of current change, and actually E is equal to minus L di dt. This L is the property of this coil, which is called inductance, and L is called inductance of the coil. Why minus N? Because this opposes the growth of current. Di dt, if it is positive, the induced potential here will be opposite time. Means Lenge's law. The Lenge's law means induced EMF will try to reduce the cause of its production. Who is there producing the induced EMF? That is the current. So it opposes the flow of current. So if di dt changes, induced EMF is opposite type, means it is sending current opposite type. So di dt, L di dt, induced potential here is opposite to IR drop. Both are different. So what we have in the circuit, you see in the circuit here we have, say E is the applied EMF, then we can write E applied EMF using the Kirchhoff voltage law. Apply EMF E, and then EMF here minus di dt, and what we have IR here. So total potential, so that is minus L di dt, because E is equal to, E is applied E minus L di dt. This potential, total potential, because E is applied here and this is opposite, this must be equal to IR drop. There is a potential across the resistance IR. Or we can write E is equal to L di dt plus IR. This is the equation. Now you can do this, say this when this I current increases, di dt, the magnetic flux here, opposing the growth of current. So this E is equal to L di dt per IR. It means the current increasing in the circuit at certain rate, and finally it becomes total current maximum when di dt becomes 0. So we were talking that if the potential of the source impressed upon resistance and inductance, the E is equal to L di dt, this is the induced potential across the inductance, and IR is the potential drop across the resistance. So this E is constant, is equal to this plus this. But as the current increases in the circuit, because in the beginning current is 0, when you press the key, current starts increasing, inductance opposes, Lenz's law. So that current increase is slow. As the current increases, I increases, IR drop increases. Means this voltage increases, total this voltage E, this increases means this decreases. That is, this decreases means L is constant, di dt goes on decreasing. So rate of change of current finally becomes 0, current change becomes 0, and circuit current becomes constant. So current takes some time to build up completely. It starts from 0, it reaches to maximum, and finally this becomes 0 and E is equal to IR. So this is the equation. Well, this L di dt becomes 0 then when current is constant L di dt becomes 0. And this, so this is 0 means the potential is, current becomes I is equal to I naught. Maximum current, that is the maximum. This means this is maximum, di dt, this is 0. So E is equal to I naught R. That is the, or I naught, maximum current I naught is equal to U over R. This is the maximum current of the circuit. Well, so what you can say? You can say that current changes, or you want to draw a time dependent current, how current increases. Well, you can see that I can draw a graph here that will show you as the time increases here. I will again explain in detail. The current starts increasing from 0, and this means this is I naught, maximum. It takes a very large time. It will never become constant 0. It is exponential like this increase. I will solve this equation. I will get the solution of this also later on. But this looks to be the time and current. So finally, at large t, it becomes I naught. But we will see this differential equation also we will write later on. But at present time, this is the circuit, and let us do current growth of the current in the circuit. Let us do some mathematical or differential equation solution to get the current for this. I can rub this so that I can write something here. Now see that we can do now the, according to Kirchhoff voltage law, we have written the equation. According to Kirchhoff voltage equation, what we wrote earlier, the same thing I write it again. I can write that E minus L di dt is equal to IR. This is the equation. Or E minus IR, E minus IR is equal to L di dt. So what is the, we can write dl over L, you can see, for integration, you can E minus IR is equal to L di dt. So di E minus IR, this like here di, and this side we write is equal to simply dt upon L. You can write like this. And multiplying both sides by minus R. Multiply both sides let me change those. Multiply both sides by minus R. This. So what you will get? This is a minus R, we multiply, this becomes minus di E minus IR, and this side is minus dt over L, and of course R. This is now integrating both sides we get, yes, integrating both sides we get, this side we integrate, so this is, you write integrating both sides, R we have multiplied by R, so where is R? Minus R. So you can write R di, and here minus of course E minus IR is equal to R over L. So when we integrate this, we write this. This is the log, on the base E or ln, log on the base E of E minus IR. And on this side, minus R over L into T plus a constant of integration. From this, well, you can get the constant by writing the boundary condition or initial conditions. So constant can be determined by writing the initial conditions. You can write the initial conditions. What are the initial conditions? Initial conditions are that t is equal to 0, I is equal to I is equal to 0, no current at t is equal to 0, and so t is equal to 0, I is equal to 0, you get, so put this condition, what you get? We get t is equal to 0, this is 0, I is equal to 0, so log E is equal to C. This means that you got now constant and you can get the solution, this equation can be converted into simply log of E minus, so E, or you can write say, so log E minus IR is equal to minus R over L T plus constant is E itself. So now what you will get? This you can take minus on this side, so log E over E minus IR over E is equal to, this becomes on base E. E minus IR, this becomes minus log E, or like this, division log E is equal to minus R over L and T. So this is simply, you take the anti-log of this or remove the exponential, then this becomes E minus IR. E minus IR over E is equal to e to power minus R over L into T. Or you can write this E minus IR. E minus IR is equal to so I is equal to, you get here, I is equal to E over R I is equal to E over R 1 minus E R by N into T. This is the solution of this equation. Means I, you calculate I is equal to, so just combine this together, you get this equation. That this is the exponential equation. So this shows exponential increase of current. That I have shown the graph. And this is the mathematical equation which I have shown the graph. That exponentially the current increases, and obviously that was the equation that I have shown earlier at time t here, and this was the how to increase this. So this was maximum current I note here. This is I, this is T. This represents E over R 1 minus E to R minus R by N into T, this equation. So this is I naught is here, maximum. I naught the value is maximum. that is I naught is equal to, this is E over R. Maximum value is when t is infinity, this becomes 0. So this is the E over R maximum current. So infinite time, at infinite time current becomes constant, and that is E over R. I naught. So this is say I naught. So E over R equal to I naught. It takes infinite time for current to become constant. I know. We can write the equation. In terms of I, we can write that E over R is I at any time. That is the maximum value of E over R. So we can write that I is equal to, here we wrote I is equal to I naught, that we are writing I naught, e to power minus R by L T. This is actually, 1 minus. This gives exponential increase of the current. Current becomes maximum. At t infinity, this becomes 0. So current becomes maximum. So R over L has the units of 1 over T or L over R. Units of time. So that this R over L is 1 over T, this becomes dimensionless. This is just number. So L over R is units of time. It is called time constant. L over R is time constant of the circuit. It has dimensions of time, that how the current builds up and how much time current takes to become constant. So that is the time constant. This is called time constant, or we write lambda. Lambda is equal to L over R. Time constant. The transient current, how transient current build-up takes place in LR circuits. This shows that how the current increases like this. So, okay. This was transient for LR. So we will discuss later on some other, but let us have some problem also connected with this LR circuit. Say, the time constant of a certain circuit was found to be 2.5 milliseconds. So this is the problem. The time constant of a LR circuit is found to be L over R. The value is given here, 2.5 milliseconds. With a resistance of 80 ohm, with the resistance of 80 ohm added in series, the time constant becomes .5 milliseconds was obtained. Because R increases, it decreases. So they have added resistance, the time constant from 2.5, it becomes 0.5. So that means find the inductance and resistance of the coil. This was circuit of LR means coil circuit. A coil we have applied some potential, so inductance and resistance of the coil. So that means coil. The time constant of LR circuit. LR means there is an inductance coil. It has got resistance, it has got inductance, and its LR, its time constant was found 2.5 milliseconds. Now they added resistance R, then it becomes 0.5. So find out L and R. That's just simple mathematics. So lambda is equal to L over R. This is equal to 2.5. We know in the beginning. And again, L over R plus 80 ohm. This resistance increase, it becomes 0.5. So this is two simple mathematical equations. Now just you can see from this, these two equations, R plus 80 divided by R is equal to 2.5 divided by 0.5. Means you are dividing this equation by this equation. So we get R plus 80 by R is equal to this. And just solve this equation. You will get L gets cancelled. So from this you get, this is say 5. So 5R and R plus 80, so 4R is equal to 80. R is equal to 20 ohm. So R you get 20 ohm, and find out L by R 2.5. From this, L over 20 is equal to 2.5. Well, L is equal to 2.5 into 20. So that gives you about 50. And the units of inductance is Henry, H. Alright, Henry. So the circuit, simple problem you can solve, and from this you get resistance 20 ohm and resistance of coil 20 ohm and inductance 50 ohm. Fine. Another circuit is, say, another calculate the back EMF. Calculate the back EMF calculate the back EMF of a 10 Henry 20 ohm, 200 ohm coil, a coil of back EMF is about 10 Henry is the inductance, 200 ohm is the resistance of 50 millisecond, 40 millisecond after a 100 volt DC supply is connected. After a 100 volt DC supply connect means when we put the switch on, after that 100 volt voltage is connected, we apply after 40 milliseconds of the connecting the, what is the EMF? So that you do, and you know that I is equal to I naught 1 minus e to power minus R over L and T. So in this, I naught is maximum current is the 100 volt divided by R. R is 200. So it is 0.5 ampere. Maximum current is like this. Lambda is equal to L by R, time constant. Lambda is equal to L by R. So L by R is how much? 10 over 200. So this we get 10 over 200 means 0.05. 0.05 seconds. And after how much time we want? Time t is equal to 40 milliseconds we want. So now you get current. I is equal to I naught, that is 0.5, I naught 0.5, and 1 minus e to power minus R over L. R over L means this 1 over 0.05 into T. T is 40 milliseconds. So that is, and 40 milliseconds means T is equal to 0.04 seconds. So this is now R over L, that means, and 0.04 divided by 0.05. So this becomes how much? I is equal to 0.5, 1 minus e to power, this is 4 over 5, and 4 over 5 means 0.8. So e is minus 0.8. So e to power 0.8, and you can see this from the table, and you multiply this, so this becomes, the answer becomes 0.275 ampere. So current after 40 milliseconds of this circuit starts becomes 0.275 ampere, but I naught is 0.5 ampere. So this is after 40 milliseconds. So we get this current. And now you can back EMF you want to calculate. So E is equal to IR plus L di dt. This we know. So from this we get E is equal to 100. 100 would be applied. IR is 0.275 after 40 milliseconds, and R is 200 plus LDI. So this gives you back EMF. We are going to calculate back EMF. That is the Lentz's law. The inductance giving back EMF. How much back EMF? LDI dt. That is the induced potential. Is equal to 100 minus 0.275 into 200. So this gives you 45 volt. So the back EMF is 45 volts. This is the answer of this question. So this type of questions we shall solve. And friends, I will stop here. This is the article, complete article, that is the inductance and resistance. Next time when we meet, we will discuss the capacitance and resistance, RC circuit. RC circuit transient means charging and discharging of condenser. So thank you very much for listening to me. Next time we will. Okay.